Week 12, Part 8, Negative or Diverging Lenses. So we've seen the ordinary kind of lenses that focus rays down to a point like this, and we call that the focal point, and this the focal length. These are what we'd call converging or positive lenses. Parallel rays get focused at the focal point. But there are other kinds of lenses as well, and here's one type. This is a diverging lens. You put it into the beam and the rays don't converge to a point, they diverge out here. They're spreading out. So it doesn't look like they form an image at all. And you might wonder, what would you do with such a thing? And how would you define a focal length for such a lens? Well, we can actually do lots of things, and we can even define a focal length. So let's draw that situation again. So here's our lens. And I'm going to draw the center line through there. And then the rays are diverging from that point. Another set of rays right in here. And the question is, where is there an image? These rays never come together anywhere, but they do, in fact, form an image. It's a little tricky to see the image, although not any harder than it is with regular lenses in certain cases. The image that's formed comes from the fact that these rays, though they are not crossing each other, they all seem to be coming from a point back here. If you draw these rays and extend them back, it looks like they all originated from a spot back on the other side of the lens. And that is what we call the focal point for this lens and the focal length, except that we call that a negative focal length because it's on the wrong side of the lens. Instead of these rays converging to a point over here, they're diverging as if from a point over on this side. So that's what we call a negative focal length. And just like with the positive lenses, there's actually an equivalent one over on the other side of the lens. And I have to draw a different situation to explain how that one works. That focal point is the place that if rays coming into the lens are aimed toward that point, then they come out parallel. That's what it does. So rays that come in as if they're going to hit that point over there, they come out parallel. And once again, if you think about it, what would be the object distance for that? Well, these rays aren't coming from a point out here and spreading out, a place to measure an object distance over here like we normally would. These rays are heading as if to a point on the wrong side of the lens. So once again, the object distance would be negative in that case. The focal length is negative. Everything works out though, and you can still use the regular lens equation. Let's work an example to show how this all behaves. So let's imagine that we have an object out here somewhere, and it's a little ways from a negative lens. And I'm going to say that it's 60 centimeters away from a negative lens. And this lens has a focal length of minus 35 centimeters. Okay? So now the question is, where is there an image? Minus 35, so that would be on this scale maybe about there and out here somewhere. Those would be the two focal points, but remember they're negative ones. So what happens to the rays? Let's just quickly sketch in what's going to go on. This ray that's heading parallel to the optical axis, that's going to be very much like this first example up here. Parallel rays diverge as if from the focal point on the left. And so that ray is going to keep going as if it were coming from that point. What else can we draw? Well, you can always draw a ray through the center. That doesn't do anything. And right there you have enough to figure out where the image is. It's right here where these two cross. There's one other ray we could kind of figure out. It's a little hard to put in here, but the ray that's trying to go toward that point, that ray would come out parallel. And then you could trace it back to the same point. That's where the image will form. Now let's do it with math. So our equation in general is 1 over S object plus 1 over S image equals 1 over F. The object distance is 60. That's nothing unusual. The image distance we're trying to figure out, the focal length is minus 35. So you can solve this. 1 over the image distance is going to be minus 1 over 35 and then minus 1 over 60. And what you'll find is the image distance is minus 22. That's what you come out with in this case. And that looks about right. If that's 35, that looks like it might be about 22. What if we were to try to figure out the magnification in this case? That's an interesting puzzle. Magnification, well, if you remember, that's either the height of the image divided by the height of the object, but we don't have that information. But we do have distances, and we have a formula for that, minus S image over S object. So let's put in the numbers, minus, now the image distance, that we just calculated, that's minus 22. So we've got two minus signs in here. The object distance was just plain old 60. And so we come out with a magnification. If you calculate that out, you get 0.37. So it's less than 1, which is why this is much smaller than the object. Now, it is a virtual image because of the fact that the rays forming that image are these rays out here. And these rays don't, in fact, go through this point over here. It's only dotted lines extended backwards from them that go through that point. So this is a virtual image. You can see that it's upright. You can also tell that from the magnification being positive. So it's upright, it's virtual, and it's also smaller. That's because this is less than 1. How would you see such an image? If you tried to put a piece of paper here, nothing would happen. You wouldn't see anything on the piece of paper. To see that image, you'd have to be standing or looking from this side over here. I'm going to try and draw a person here. Here we go. Here's our person who's looking, and they're looking at these rays. These rays would be getting into their eyes, and they would be able to see this point here. They would not see the original object. They'd see it right here, and it would look very small.